Models of the atom. Here are some of the various models of the atom. The Thomson model goes back to the early 1900s, and it really represented the fact that they knew that they had positive particles and negative particles, and it made the most sense at that time to think that they would be just randomly distributed because they knew that positive particles did not like each other. Like charges repel and unlike charges attract. So they thought that they were just sort of distributed like you would have chocolate chips and nuts in a cookie. Later, Rutherford's experiment in the again the early 1900s showed that when a positive particle was thrown towards an atom, most of the particles went straight through, and only a few of the particles that got close enough to what he determined was a nucleus could be repelled or deflected either a little bit or deflected all the way back. And that's what they talk about in the video about the atom. Because there was about 1 for every 10 to 20,000 particles, they realized that the size of this nucleus was extremely small, and also that this nucleus was positive. So we have the protons that are in the nucleus, and then the electrons are in what we call the electron cloud. Now, just in the development of the picture of the atom, that electron cloud has changed quite a bit. Early representations of the electron cloud had the electrons in nice little orbits as if they were planets going around the sun, which could be represented in this model or even in this model right here. And one of the reasons for this was they realized that if the electron or if the atom absorbed energy, that electrons could be somehow promoted, absorbing that energy, and then they could fall back down to their original energy level again. And these are stepwise. They are not a continuous ramp of energies. And they actually have, for each atom, they have spectra, and each of these colors represents a difference in energy level. This would be the smallest difference in energy level, for example, between these two spots perhaps, and larger differences in energy levels are represented by the shorter wavelengths, the purples and the ultraviolets and so on. So this model, the Bohr model, is actually used to explain a lot of spectroscopy, even though it is no longer considered that the atom is quite so simple. This is another model where you can see that we've now added neutrons, which were not discovered until about 1932. So we have a nucleus that contains protons plus neutrons, and then we have electrons in this cloud. Now, more realistic is this modern picture where you have the protons and neutrons in the nucleus, and then you have the electrons distributed, and they are randomly distributed. There tends to be areas where they tend to be. Notice there's a higher density in this area than there is in the other areas around, but the electrons can be anywhere. They do not have to be in a specific orbit. And what we're really looking at with these changes is energy changes, not so much distance changes. For most of the work that we do in general chemistry, this is the model that explains a lot of things that we will do. And we will actually use this model, but you need to realize that it is not this simple, and that this model is probably more realistic, but it is a lot more complicated to explain any of the processes with. So do realize that there's been a sequence of change in the models of atoms.